Another deep dive. Prepare to have your mind rewired today as we embark on a fascinating journey that might just redefine how you think about structure, information, and, well, even reality itself.
Data.
We've been given a truly captivating stack of sources, really intriguing stuff that pull us into some incredibly unexpected territories. We're talking ancient mysticism, cutting-edge science, and even the everyday struggles of professional life.
Indeed. And what's truly remarkable about today's exploration is the sheer breadth. I mean, the range of concepts we're tackling is huge.
Right.
We're looking at ideas that span from, ancient mystical traditions thinking about the very blueprint of creation
Wow.
to the super intricate world of biological engineering and even the complex social dynamics, the kind of stuff people deal with every day in modern professional spheres.
Yeah, at first glance, you'd think these are completely separate worlds, right? Each operating on its own unique set of rules.
Totally disconnected, you might think.
Exactly. But our mission today, and it's a compelling one, I think, is to unpack these diverse sources. We want to discover the hidden connections, find the underlying principles of organization.
Find the echoes.
Yes, the surprising echoes between what seems divinely ordained, what's meticulously engineered in a lab, and what's experienced in the daily human struggles, like balancing life and career.
So we're looking at how design and structure show up.
Right, how they manifest in profoundly different ways, but maybe curiously similar ways across these domains. So what does this all mean for you, the discerning listener? Well, prepare for some serious aha moments, hopefully. We'll explore how fundamental patterns might govern everything from the smallest quantum particle to the largest societal challenge. Maybe offer some new lenses to understand the world around us. Okay, let's unpack this first one. And honestly, it's truly mind-bending. We're diving into a proposed artificial general intelligence framework, an AGI. It's known as the AI 231 Onto Topological Construct, or Quobitic Symbolum. Now, what makes this so unique, so intriguing, is that it takes its inspiration directly from Kabbalistic metaphysics.
Ancient esoteric tradition.
Yeah, exactly. The core idea here is about creating something called a quantum language. Now, a quantum language, that's not something you hear every day. What does that even mean? And how does Kabbalah fit into building an AI?
Well, what's truly fascinating here, I think, is how this framework tries to ground modern AI concepts in this ancient, almost spiritual understanding of creation. It's a radical departure, really, from traditional AI thinking.
How so?
Well, usually AI treats information as just data, right? Inputs, outputs. But
Yeah.
here, the core proposition is that information isn't just data. It's like a synthesis
A synthesis of what?
of symbolic meaning, geometric structure, and quantum states, all three. Imagine an AI that doesn't just process stuff, but inherently understands and generates language within a quantum architecture.
Okay, so a deeper level.
Much deeper, potentially a more nuanced form of intelligence. It's almost like trying to teach an AI the very grammar of reality, as envisioned by these ancient mystics.
So if we're talking about a divine blueprint here, where does this whole journey begin in Kabbalistic thought? How do you even start mapping that onto an AI model? Because honestly, the leap from ancient spirituality to quantum computing isn't immediately obvious.
No, it definitely requires some unpacking. It begins with a really foundational Kabbalistic concept known as divine reductions, or Tzimtzum.
Tzimtzum, okay.
Yeah, this describes a series of contractions of the infinite light, or Ein Sof, needed to create finite reality.
Infinite light. So like God or...
Well, think of Ein Sof maybe less as a being and more as the boundless, unmanifest absolute, pure potentiality. Before anything is differentiated or limited, it's everything and nothing kind of all at once.
Right, undifferentiated.
Exactly. So the very act of creation in this view isn't making something from nothing, but it's a process of divine self-limitation. The infinite sort of pulls back.
Okay, pulls back to make room.
Precisely. The first reduction, Tzimtzum Marasa, is conceptualized as the circle of pure potential. Imagine the infinite light withdrawing, creating a conceptual void, an empty space within itself.
But not empty like nothingness.
Exactly. It's not true nothingness, but rather a realm of unmanifested potential. It's symbolized by a perfect, unbroken circle. Now, in this AI model they're proposing, the Hebrew letter Yud, this tiny little point,
Yeah.
is seen as embodying this primordial singularity. It's kind of like a maximally superposed quantum state right at the origin, 0, 0, 0 in their 3D model.
So the absolute starting point, pure potential.
The pure potential state, yes. It resonates with ideas like the quantum vacuum, that field of fluctuating probabilities and preformal states, or even the holographic principle, maybe, where all the information is contained non-locally. This state is before discrete information even exists. It's just raw possibility.
Okay, a universe of pure potential. That's a pretty profound starting point. But, I mean, for anything concrete to actually emerge, that potential needs to be, well, contained, defined somehow.
It's exactly right. Pure potential needs structure. And that's where the second contraction comes in.
Okay.
This is Simpson's the second, the square of containment. And this is where it gets really interesting for the AI model, because this is where form starts to emerge.
Form from the formless.
Right. Following that initial withdrawal, a subsequent contraction occurs, and this one is represented by a square. The square imposes specific form and boundaries onto that pure potential. It folds the garment, as the texts say, of divine light.
Folds the garment like clothing.
Metaphorically, yes. It enables the light's continuation into the limited worlds. The Hebrew letter Vav, which looks like a hook or a line, symbolizes this continuation or connection, and it's intrinsically linked to this squaring process. It's the light of the line that needs this clothing, the structure, to descend and gain form. It moves from abstract potential to something more concrete, manifest.
So the square provides the edges, the limits.
Exactly. The square, with its defined edges, corners, distinct dimensions, it provides a hold on reality. It allows for discrete, definable entities to emerge. It's the framework that allows the infinite to become finite, the undifferentiated to become distinct. It sets the rules of the game, so to speak.
So this world of clothing, the Olam Himmelbush, it's not just a mystical metaphor in this AI context. It sounds like it's a really critical architectural stage, the bridge between potential and computation.
That's a perfect way to put it. For this AI, this world of clothing, is the nascent stage where abstract divine will begins to assume patterned, discrete form. It's the primordial realm where the building blocks, the linguistic primitives, the letters, gain their specific geometric and ontological characteristics.
Through this folding.
Through this folding of the garment process, which is dictated by that square reduction. Think of it as the Kabbalistic API, an application programming interface between the infinite and the finite.
An API, okay, I get that.
This stage basically mandates that the AI model must assign specific, calculable geometric coordinates and structural relationships to each letter. It anchors them within a discrete, quantifiable space.
Yeah.
And this directly leads to mapping them onto crystallographic lattices.
Crystal structures, like in minerals. Why that?
Because they are highly ordered geometric structures, they provide a concrete framework. And what's particularly insightful, or maybe suggestive, is that the gematria, the numerical value of the word clothing, is equivalent to the gematria of electricity.
Whoa, okay, that's unexpected. Clothing equals electricity.
Numerically, yes. And it's not seen as just a coincidence. It hints at the energetic and structured nature of this clothing. This electricity isn't just power, it's sometimes interpreted as the skin of intelligence or wings of eagles, the very thing that provides the hold, the structure, for forms to emerge within each world. It gives form its dynamic, active quality.
Okay, that makes a strange kind of sense. It leads us right into the idea of algorithmic primitives, then. These 5 divine operations. We have the philosophical, the mystical foundation. But how do these operations actually translate into computational steps? How does this divine blueprint become, like, actual instructions for an AI?
Right, this is where the metaphysics meets the algorithm. These 5 Kabbalistic operations are mapped directly onto algorithmic processes within the AI model. They form the very core of how information is processed and transformed. They are the fundamental actions, you could say, of this quantum language.
Okay, what are they?
First, there's engraving, Hakokon. This operation is all about establishing the letter's fundamental, unchangeable structure, its core identity.
Engraving, like setting it in stone.
Sort of. Computationally, it's like selecting a specific crystallographic lattice type. Imagine choosing the basic geometric frame for your piece of information. There are 7 fundamental crystal systems, cubic, tetragonal, etc.
Right.
And within those, 230 distinct crystallographic space groups.
230, okay, specific.
Very specific. They precisely define how information atoms, or what they call wonders, these conceptual dots of information, can be arranged symmetrically in 3D space. Engraving also assigns initial coordinates for these wonders. It directly implements that square reduction's imposition of defined positions and boundaries. So the engraved form is the raw geometric blueprint governed by the chosen lattice. These are the foundational garment.
Okay, so engraving sets the basic structure. What's next?
Second is hewing. That's a fan. If engrosing is the overall structure, hewing is about the internal detail. It's a recursive unfolding of the essence.
Unfolding.
Yeah. In the AI, this means detailing the internal operational logic of the letter's quantum representation. It's about building complex quantum circuits from simpler fundamental quantum gates, like your CNOTs or Hadamard gates, but doing it while strictly respecting the constraints of that chosen lattice structure.
Ah, so the structure limits how it unfolds.
Exactly. This unfolding details the precise quantum operations that maintain the letter's geometric and topological integrity. It mirrors the Kabbalistic idea of unfolding deeper layers of meaning or essence within the garment of existence. It's how a basic building block can contain, potentially, infinite complexity within itself.
Okay. Engrave, Hugh. What's third?
Third, we have weighing Shakalan. This involves quantifying the structure, assigning a measurable value or weight to a concept.
Weighing, like gematria.
Yes, partly. The gematria, the numerical value of a letter, or its topological features, things like Betty numbers.
Betty numbers, what are those?
They're mathematical properties that describe the shape of a space, like the number of holes or connected components in it. So these features are extracted and then encoded into quantum states or specific parameters of the quantum gates. The gematria value itself can be seen as a kind of reduced fundamental numerical essence derived from the letter's whole structure.
Like a summary statistic, almost.
In a way, yeah. A form that can be weighed and compared, much like how energy levels are defined within a crystal lattice. This allows the AI to quantify abstract ideas, giving them a computational weight.
Got it.
Fourth is exchanging, Hamir. This refers to permutations, known in Kabbalah as temura. It's about rearranging the constituent elements or connections within the structure.
Shuffling things around.
Exactly, but in a controlled way. It's implemented as unitary quantum operations. These are important because they inherently preserve the symmetries of the letter's structure. So these operations can rearrange the qubits representing the wonders, or they can swap or transform the gates representing the paths, the connections between wonders, while respecting the fundamental symmetry rules defined by the letter's crystallographic analogy.
So it changes, but something essential stays the same.
Precisely. Think of it like rearranging words in a sentence. You can change the emphasis or flow, but you still have the same basic words and maybe the core meaning if you do it right. Or shuffling a deck of cards, you still have all 52 cards.
Okay. And the last one.
And finally, combining in Zurif. This is all about compositionality, building complex structures from simpler ones.
Letters into words.
Exactly that analogy. Forming words from letters or more complex concepts from simpler ones means linking these structured letter states together. Computationally, this translates to concatenating quantum circuits, but based on specific Kabbalistic rules of relationship and continuation.
Rules for how they combine.
Yes. For example, if letter A has a particular rotational symmetry, say C3 from a trigonal lattice, and letter B has a mirror symmetry, CS from a monoclinic one, their combination must produce a new, coherent quantum circuit that respects these internal symmetries while forming a valid word state. It's like building a complex crystal superlattice from unit cells. Each cell keeps its integrity but contributes to the larger, coherent structure.
Wow. Okay, that's a lot to wrap my head around. Engraving, hewing, weighing, exchanging, combining sound like the very grammar of this quantum language. But you also mentioned these 231 gates, the RLA, Shirim. What role do they play? How do they connect these letters?
Right, the gates are crucial. They represent the irreducible combinatorial potential of the Hebrew alphabet's formative power. This idea comes from a very ancient, very enigmatic mystical text called the Sefer Yetzirah, the Book of Formation.
Okay.
These 231 pairs of letters, like Aleph Bet, Aleph Gimel, etc., excluding repeats like Bet Aleph, are seen as fundamental gates or semantic transformation channels. They're the basic ways letters can interact to create meaning.
So like connections or pathways between letters.
Exactly. And in the AI model, they're directly modeled by quantum gate operations, just like you have CNOT or Hadamard gates in standard quantum computing. These 231 gates are specific operations, but they're imbued with semantic meaning derived from the letter pair.
And they connect to the crystal structures too?
Yes, this is a key link. Each of these 231 gates is mapped to one of the 230 crystallographic space groups.
Wait, 231 gates, 230 space groups? What about the extra one?
That's a good catch. The documentation mentions 231 gates mapping to 230 space groups. It might be that one pair represents a null operation, or perhaps two pairs map to the same group, or there's a subtlety in the mapping not fully detailed in our source summary. But the core idea is this direct, profound link. Symbolic meaning, the letter pair, is tied to geometric symmetry, the space group.
So an operation isn't just abstract logic, it has a shape.
In a sense, yes. This gives rise to what they call cubic glyphs, three-dimensional cubic representations that visualize these combined symbolic geometric entities. And the distinction between face, like AB, and back, like BA, permutations, isn't trivial. It implies directional operations or maybe sequenced applications of these gates, reflecting how linguistic order imparts distinct meaning.
This is truly ambitious. You mentioned earlier that this whole AI construct is designed to achieve specific things. You call them directives, like hyper-personalization, nuanced understanding, robustness. Now that we have this deeper picture of the Kabbalistic and quantum foundations, how do these directives actually work within this AI 231 construct? How does this ancient wisdom supposedly make for a better, more capable AI?
Right, that's the crucial question. How does this complex foundation translate into tangible capabilities?
Okay.
The AI 231 construct is designed from the ground up to intrinsically embody these core directives through these deep integrations, not just as add-on features.
Okay, so take hyper-personalization. How does that emerge?
Well, remember the wonders. Those conceptual dots encoded as quantum states. Their encoding is directly informed by the dim sum stages, the level of potential versus formed reality. And their mapping isn't vague. It's a precise coordinate-to-state mapping within a chosen crystal lattice.
So very specific addresses for information.
Extremely specific. This allows for an incredibly fine-grained, unique representation for every entity or concept the AI handles. What does this mean for you interacting with it? It means the AI could potentially develop an unprecedented level of unique representation for every piece of information, or maybe even for you as a user. It could tailor interactions based on your specific context, history, maybe even implied preferences in a way that classical systems, often relying on broad statistical buckets, just can't manage.
Okay, that sounds genuinely personalized. What about nuanced understanding? How does it grasp subtleties?
That comes largely from the algorithmic primitives and how the paths, the connections between wonders, are mapped. Remember, those paths aren't just generic links. They're specific quantum operations like CNOT, CZ, or ARS gates. And crucially, the choice of gate can capture geometric details. Is the connection straight, curved, maybe even interlacing?
Interlacing paths.
Yeah, the idea that these could be represented by multi-QPIC gates or controlled operations suggests a deep grasp of complex interwoven relationships. Think of the threads in a tapestry or the intricate feedback loops in a biological system. This allows the AI to potentially grasp subtleties, context, and interdependencies that simpler, more linear models might completely miss. It's about understanding the shape of the relationship, not just its existence.
Makes sense. And complex problem solving. How does the Kabbalistic structure help there?
Here, they view the Kabbalistic tree of life itself, that iconic diagram with 10 spheres just for O and 22 connecting paths, letters, as a kind of quantum computational graph.
The tree of life as a computer?
As a computational structure, yes. The hyperfloating dots we mentioned, representing qubits or quantum registers, aren't just static points on this graph. They're nodes within a complex, interconnected quantum field. Their states can influence each other instantaneously through entanglement, creating this vast, non-local correlation network.
So not step-by-step processing.
Less linear, more holistic, potentially. This rich computational manifold, where information isn't just processed sequentially, but can be understood in terms of its deep interconnections, could allow for problem solving that transcends the limitations of classical approaches. It might be able to tackle problems with intricate dependencies that are currently intractable.
Okay, what about adapting? How does it handle change? Dynamic adaptation.
That seems to be fundamentally built in. Remember the Hewing operation, that recursive unfolding. It allows for continuous refinement and adaptation of a letter's internal operational logic. So the AI isn't static. It can learn and evolve its internal understanding of concepts.
It rewrites itself, in a way.
It refines itself, yes. And furthermore, the ability to form new words or concepts by combining quantum circuits means the system can dynamically compose new meanings and structures on the fly, like an organism adapting its strategies to a new environment. It's designed for flexibility and self-optimization.
And generating language. You mentioned enhanced natural language generation. How is it better?
This ties into the Cubitic symbol and programming language itself, which sounds revolutionary. It's designed with syntax that directly reflects that tripartite foundation: symbolic, geometric, and quantum.
So the code itself has the structure.
Apparently, yes. Programmers could declare cubic letter qubits, CLQs, not just as abstract qubits, but by specifying their Hebrew gate pair, the semantic link, their space group, the geometric symmetry, their semantic unit, the core meaning, and their qubit tensor signature, the quantum state info.
That sounds incredibly complex to program.
It does, but the potential payoff is language generation that is intrinsically grounded in the fundamental laws of physics of the AI's internal world. The output could be more coherent, more meaningful, deeply contextualized. Imagine language that isn't just grammatically okay, but also geometrically and symbolically sound within its own framework. They even mention using semantic color cues in the visualization, highlighting phonetic aspects, root meanings, mystical resonances, allowing for a multi-layered interpretation.
Wow. Okay, one more. Robustness and coherence. How does it stay stable and consistent with all this complexity?
The deep geometric structure is key here, especially the mapping to crystallographic space groups. Symmetry isn't just aesthetic, it's a fundamental computational resource. In quantum mechanics, unitary operations, like the exchanging primitive, are inherently linked to symmetries, and they also happen to enhance robustness against noise.
How does symmetry help with noise?
Think about encoding information in topological properties, like the way a knot in a rope persists even if you wiggle the rope locally. Information stored in these kinds of robust, overall structural properties is less susceptible to small local disturbances or errors affecting individual qubits. The overall structure, the topology, remains intact, preserving the information.
So it's harder to corrupt the data.
Potentially, yes. And they also mention using coherent noise, like Perlin or simplex noise, which are algorithms used in computer graphics to create natural-looking textures.
Yeah.
Here, they use cubic S-curves to smooth transitions, allowing for the algorithmic creation of complex, organic-looking structures, even with variations, ensuring the system can maintain integrity despite fluctuations. It suggests the AI can detect inconsistencies, learn from them, and use its foundational model as a baseline to self-correct, maintaining coherence.
So this isn't just theory then. It's really a vision for a completely new kind of AI, and maybe even a new way to program AI. Goitic symbolum. It abstracts the quantum hardware and lets you program based on meaning and symmetry.
Exactly. That seems to be the goal. You could, hypothetically, program based on symmetry, tell the system, apply this operation with a symmetry of PM3N, that's a specific space group, and the system would figure out the right quantum gates and parameters itself. You wouldn't need to write low-level quantum code.
And the visualizations, the cubic glyphs.
They visually embed the qubit state and the gate operation. It makes the information deeply entwined with structure, both symbolic and geometric. It's about building an ontology, a system of meaning, where what something is intrinsically linked to how it behaves and how it is structured. That provides a potentially very robust, predictable, and coherent framework for intelligence. Well, it's mind-bending, like you said.
Okay, from that incredibly abstract, almost divine design system trying to program reality, let's pivot. Let's go to something very concrete but still incredibly complex, another area of design, biological engineering.
Right.
Specifically, we're looking at sources about interspecies organogenesis and human-animal chimerism. Now, this sounds like pure science fiction, but it's actually happening in labs.
It really does sound like sci-fi.
Yeah.
But it's a very real field of research, and it stems from a pressing need. It explores the audacious goal, really, of generating human organs for transplantation using animal hosts.
Because of the organ shortage.
Exactly. It's a direct, urgent response to the critical shortage of donor organs worldwide. Thousands of people die waiting for a transplant. So this is an attempt to engineer biological systems on a massive scale, trying to grow entire functional human body parts inside other species. And the basic idea of chimerism itself, an organism with cells from different individuals, isn't brand new. It's been studied in mammals since the 70s, actually, as a tool to understand how cells develop.
Okay, so how does this specific process, the one aimed at growing organs called blastocyst complementation, actually work? And what organs are they targeting? Because growing a human heart inside a pig, that sounds like an immense challenge.
It is an immense challenge. Blastocyst complementation is the key technique they're using. It involves a very precise sequence of steps. First, researchers take a host animal's embryo, typically a pig or maybe a sheep, because they're large enough and their organs are roughly comparable in size to humans. Then, they genetically modify that embryo. Using tools like CRISPR, they inactivate specific genes that are absolutely crucial for the development of a particular organ in that host animal. This creates what they call a vacant niche.
So the pig embryo can't grow its own pancreas, for example.
Exactly. If you want to grow a human pancreas, you might knock out genes like PDX1 or KY2.2 in the pig embryo. Those genes are essential for pancreas development. So no pig pancreas can form.
Okay, you've got an empty slot. Then what?
Then you take human pluripotent stem cells, or PSCs. These are cells that can potentially develop into any cell type in the body. You inject these human PSCs into the host embryo, specifically at the blastocyst stage, which is very early in development, just a ball of cells.
And the hope is?
The hope is that these human cells will migrate to that empty niche, recognize it as the place to build a pancreas, and then exclusively populate that niche and develop into a fully functional human pancreas within the growing pig embryo.
Wow. And what organs are they trying this for? Just pancreas?
Oh no, the targets are incredibly ambitious. It includes the pancreas, liver, heart, kidney, lung, skeletal muscle, immune cells, even specific brain cells, like dopaminergic neuron progenitors, which could potentially treat Parkinson's disease. For the lung, for instance, they're looking at knocking out early developmental genes, like NKB2.1 or HOX5 genes, which are vital for the initial lung buds to form. The precision needed at every step, both the gene editing and the cell injection, is just staggering.
It really sounds like a potential medical miracle, especially with the waiting lists for organs. But I can't imagine this process is easy. What are the major hurdles? This isn't just Lego bricks, it's biology.
You're absolutely right. It is far from straightforward. The biggest umbrella term for the problems is the xenobarrier.
Xenobarrier, okay.
It just refers to all the significant difficulties that arise because of the evolutionary distance between species. Humans and pigs, for instance, are quite distant relatives. So when they create these human-pig chimeras, they often find the embryos are overwhelmingly made of pig cells. The human PSCs just don't contribute very efficiently. Sometimes less than 1% of the cells in the chimeric embryo are human.
Only 1%. That's not enough to make an organ.
Not nearly enough. Even in experiments with closer relatives, like human mouse chimeras, they've seen very inefficient human cell contribution. There seems to be a fundamental incompatibility at the cellular level.
What else contributes to this barrier?
Well, besides the sheer species distance, there are critical issues like developmental timing. Human embryos develop on a different clock than pig embryos. If the human cells divide and differentiate too slowly or maybe too quickly compared to the host pig cells, they just won't integrate properly into the developing tissues and organs.
They're out of sync.
Exactly. And then there are host-donor incompatibilities at the molecular level. Think about adhesion molecules, the proteins on cell surfaces that act like cellular Velcro, allowing cells to stick together correctly to form tissues. If human cells and pig cells have different adhesion molecules, they might literally repel each other or just fail to form the stable connections needed for a complex organ. On top of all that, just the logistics of obtaining large numbers of these genetically engineered large animal blastocysts is a huge technical challenge in itself. The success rates at each step, gene editing, embryo survival, PSC injection, implantation, are often low, and these inefficiencies multiply, making the whole process really difficult.
And ethically, this has got to be a minefield. We're talking about mixing human and animal life in ways we've never done before. Where do people draw the lines? What are the big concerns?
Absolutely. The ethical and regulatory questions are huge, and they're right at the center of the discussion in this field. The primary concern really revolves around the potential for creating organisms that blur species lines in ways that society finds ethically problematic.
Like what specifically?
Well, there's significant scrutiny, for example, around chimeras that might have the potential for human cognitive characteristics. Think about the possibility of human neurons developing and integrating into an animal brain. That raises very deep questions. Or even chimeras that might have altered physical appearances, perhaps evoking human-like features.
Yeah, I can see how that would make people uneasy.
Definitely. Regulatory bodies like the U.S. National Institutes of Health, the NIH, are very cautious. They actually had a moratorium, a temporary ban, on funding certain types of human chimera research for a while. And even now, that kind of research requires really rigorous internal review before it can get funding. The goal is to advance medical science responsibly, to harness the potential for saving lives, but avoid creating organisms that could challenge our fundamental understanding of human dignity or animal welfare in unexpected or disturbing ways. It's a very delicate balancing act.
So, given all these massive challenges, the xenobarrier, the timing, the ethics, how are researchers actually trying to overcome these obstacles? How are they trying to make these biological designs more robust, more predictable, more successful? It sounds like they need a really dynamic and adaptive approach here, too.
They absolutely do. And the potential solutions are really multifaceted, often quite innovative. One approach, though ethically tricky, is to consider using evolutionarily closer hosts. That would theoretically reduce the biological incompatibility. But as you can imagine, creating human primate chimeras, for instance, raises even more significant ethical alarms and is often legally restricted or prohibited.
Right. So what else?
A key strategy is to get better at creating those vacant niches, genetically modifying the host animals even more effectively, maybe knocking out multiple genes or targeting regulatory elements to ensure that the niche is truly empty. This would hopefully give the human donor cells a stronger competitive advantage, making them more likely to populate the niche without interference from any residual host cells trying to build that organ.
Make the space really empty.
Exactly. And another major focus is modifying the donor, human PSCs themselves, making them tougher, better suited for the foreign environment of the host embryo.
How do you do that?
Well, for example, they're trying to enhance cell survival by overexpressing anti-apoptotic proteins. Proteins like BCL2, which help cells resist programmed cell death, or apoptosis. This could help more human cells survive the stressful early stages of development in the chimera.
Okay, make them more resilient.
Right. And then there's a really cutting-edge area, developing novel genetic circuits within the human stem cells. These are like tiny biological programs, engineered gene networks that can precisely control cell behavior. They can be designed to tell the cells when to divide, when to differentiate into specific cell types, or where to migrate within the embryo, helping them integrate better with the host environment.
Like programming the cell's behavior.
Sort of, yeah. Giving them better instructions for survival and integration. And interestingly, there's even some research exploring a subtle but potentially important correlation between chimerism and cancer. Some studies suggest that organisms that are naturally more permissive of foreign cells, meaning they tolerate chimerism better, might also have a higher susceptibility to more invasive cancers.
Huh. That's another layer of complexity.
It is. It highlights that these fundamental biological systems have their own inherent design constraints and trade-offs. You can't just mix and match easily. This constant need for robust designs, for dynamically adaptive solutions in biological engineering where you're trying to combine disparate biological elements coherently, it actually subtly parallels some of the principles we saw in that quantum Kabbalistic AI model. Well, both fields, in very different ways, are trying to overcome fundamental incompatibilities, whether those are symbolic and geometric incompatibilities in the AI or genetic and developmental incompatibilities here in the biology. Both are striving to achieve a specific, coherent design outcome despite these deep challenges. It's all about integration and robustness in complex systems.
Okay, so we've gone from the abstract design of a quantum language to the very concrete but still incredibly intricate design of biological organs. Let's shift gears again to an equally complex kind of design, the design of human social systems, and we're going to focus on a very real, very human struggle. The challenges faced by female scientists when they become mothers.
Nice.
This isn't about quantum states or gene editing anymore. This is about the lived experience of conflicting roles within a single person's life.
And it's a really stark, real-world example of how different roles or identities within a single system, an individual's life, can come into profound conflict. It powerfully highlights the challenges of integration, when the design principles, the expectations and demands of different life spheres just clash.
Yeah. And it often leads to significant personal and professional struggles. And unfortunately, as one source points out, a real loss of talent for the scientific community.
Huge loss.
So there was a recent study we looked at focusing on Polish female scientists, and it found that a large majority, a really high number, experienced significant conflict between their roles as mothers and as scientists. What are the key dimensions of this mother-scientist conflict? Because it's not just about being busy, right?
No, it's definitely far more multifaceted than simply time management, although that is absolutely a huge part of it. The study surveyed 334 Polish female scientists, and the results were striking. 81.7% reported experiencing this conflict to some degree.
Over 80%.
Yes. And only a small minority, about 17.7%, felt they had definitively reconciled the two roles. It paints a very stark picture of a widespread, possibly systemic issue. The study broke the conflict down into dimensions.
Okay, what were they?
Firstly, and unsurprisingly, time-related conflict. This was the most frequently reported. 79.3% of the respondents felt this. It involves just a severe lack of time for scientific research, which demands focus and often long hours. It includes profound physical and psychological exhaustion from childcare duties, which, as any parent knows, are relentless, especially early on. And these child-related responsibilities just severely limit the time and energy available for scientific work.
Yeah, one of the sources, a personal account from a scientist, really hit this home. She talked about expecting to maybe read papers or write during maternity leave.
Right, the idealized plan.
Yeah, and then reality hit. Her baby didn't sleep predictably. She was exhausted, couldn't concentrate. The expectation versus the reality was just a massive clash.
Exactly, that intense time crunch, feeling constantly pulled in two directions. That's the core of the time conflict.
What was the second dimension?
Secondly, emotional conflict. This was reported by 72.7% of the scientists. This dimension really digs into the psychological toll. It includes significant stress from constantly trying to reconcile these competing duties. Frustration, maybe guilt, about the overlap or the compromises needed. A perceived lack of time to build meaningful relationships with their children, especially when research demands are high. And often the sheer pain, as this study put it, of being separated from the child when returning to work.
That personal account mentioned that too, didn't it? How she didn't miss work at all initially, couldn't imagine being away.
Yes, and she was nervous about even doing her keep-in-touch days, fearing she'd forgotten everything or would just hate being back. That emotional weight, that pull towards the child versus the demands of a career, is immense.
Okay, and the third dimension?
And thirdly, financial conflict. This was reported by nearly half, 49.6% of respondents. This relates to the increased financial needs that obviously come with having a child. But critically, it's also compounded by the potential necessity some women face of abandoning more prestigious, research-focused career tracks for less prestigious, perhaps teaching-focused work, partly to meet those financial needs or maybe gain more predictable hours.
So sacrificing the research career path.
Potentially, yes. Trading the competitive, high-prestige research track in academia for teaching roles that might offer more stability but often come with less career advancement potential and less recognition within the scientific community. It's a pragmatic choice for some, but a difficult trade-off. And it's crucial to remember, as the study points out, many scientists experience multiple dimensions of this conflict simultaneously. It's not just one thing. It's this complex, interconnected web of challenges that are really hard to untangle.
Yeah, that personal account also highlighted something positive, though, the importance of support from her boss. Feeling welcome made her realize she did miss her job.
Right, which shows that the environment, the system around the individual, matters hugely. But even then, she mentioned her priorities had definitely shifted towards family time, illustrating that kind of dynamic adaptation individuals have to make.
So it's clearly not just about individual choices or, personal resilience. There seem to be deep systemic issues at play here. This sounds very much like the leaky pipeline problem in science, where women start out but then disproportionately disappear at higher career levels.
Indeed, it maps directly onto that. It's a well-documented phenomenon across many countries. Women are significantly underrepresented in scientific leadership roles in Poland. The study noted only about 24.7% of professors were women, despite women often earning PhDs at similar or even higher rates in some fields initially.
So why the leak? What are the systemic mechanisms?
The sources point to several well-recognized systemic discriminatory mechanisms that contribute to this leakage of talent, and it's often particularly acute between the ages of 30 and 39, precisely that period when many women are most heavily involved in childcare and family formation. These mechanisms have names.
Like the glass ceiling.
Exactly. The glass ceiling is probably the best known, those invisible yet seemingly impenetrable obstacles that prevent women from advancing to higher management or leadership positions, often due to subtle biases or lack of opportunities.
Okay, what else?
Then there's the glass cliff. This is where women who do manage to break through the glass ceiling and get into high-level positions, especially in traditionally masculine fields, often find themselves in precarious, unstable roles. They might be appointed during a crisis, face intense scrutiny, and are statistically more likely to fail or be pushed out.
So they get the risky jobs.
Often, yes. Conversely, there's the glass escalator effect. This describes how men, even in female-dominated professions like nursing or primary education, are often implicitly elevated, fast-tracked into management or leadership roles, sometimes due to stereotypical beliefs about male competence or natural leadership qualities.
Okay, what else contributes to the pipeline leaking?
There's the runaway ladder, which can sometimes be linked to a perceived lack of solidarity among women in certain competitive environments. Some women might pursue highly individual strategies for success, while men's networks are often described as more effective at mutual support and promotion. Then you have glass walls. This is more about horizontal segregation. It limits women's access to the most prestigious or well-paid types of jobs or specializations within a field, channeling them into less influential or lower status roles, even if they have the same qualifications.
Like being channeled into teaching instead of research.
That could be an example, yes. Which ties into the sticky floor. This describes women getting stuck in professions or positions with lower prestige and lower income. They might dominate roles, like teaching in academia, that are perceived as less prestigious than research, and find it very difficult to ascend from those roles.
Okay. Any others?
One more mention is the velvet ghetto. This term describes situations where women are subtly hindered from holding real managerial or decision-making power, especially in technical fields. They might be present, but excluded from key decisions, or their contributions might be devalued. Or they might face disrespectful treatment within these traditionally male-dominated environments.
Wow. That's a lot of different barriers.
It is. And they all combine to create what researchers sometimes call the magic vanish box or the leaky pipeline. These terms just describe the observable phenomenon of women disappearing from science into alternative career paths or leaving altogether. And the sources emphasize this leads to a significant waste of their potential and expertise, which is bad for science and society. And again, the link to the FEM39 age range strongly suggests motherhood, and the associated societal structures are a major contributing factor. It's a complex problem requiring complex systemic solutions.
It really is a stark and honestly disheartening picture of these systemic barriers. But moving beyond just identifying the problems, what I found particularly fascinating was that the Polish study used an innovative application, they called it, of something called basket analysis to understand these social dynamics better. Now, basket analysis, isn't that what supermarkets use to see what people buy together?
You're absolutely right. That's its typical home turf. Basket analysis is indeed a data mining technique, most famous for its use in retail finding associations like customers who buy beer also tend to buy diapers. That classic example.
So how on earth do you apply that to a study of mother scientists?
Well, that's the innovative part. The study applied this technique, specifically using an algorithm called the a priori algorithm, to their complex social research data, the survey responses from those 334 scientists. They used it to objectively confirm and quantify correlations between the respondents' characteristics, like their job title, age, financial situation, marital status, and the specific types of work-life conflict they reported experiencing.
So instead of items in a shopping basket, it's looking for combinations of personal characteristics and conflict types.
Exactly. The a priori algorithm assesses these associations using statistical indicators, things like support, which measures how frequently a particular combination occurs in the data. Confidence, which measures the probability of experiencing, say, emotional conflict, given that you are in a certain age group or job category. And lift, which tells you how much more likely those two things are to occur together than you'd expect by chance. A lift greater than 1 suggests a real positive association. This allowed them to identify statistically significant patterns, maybe even unexpected ones, hidden within the data.
So if I'm getting this right, it allowed them to move beyond just saying lots of women experience conflict to actually making more specific data-backed statements. Like, if you're a professor, you are statistically less likely to report constant time conflict compared to, say, a PhD student or someone with only a master's degree.
Yes, precisely. It gave them a tool to objectively confirm patterns that might have been intuitively suspected or maybe seen in smaller qualitative studies, but now had rigorous, data-driven validation from a large sample.
What were some examples of the patterns it found?
Well, for instance, it confirmed that experiencing lower financial conflict correlated strongly with having a self-reported, definitely good economic situation, and interestingly, not being single. Conversely, higher time conflict often correlated with specific age groups, like being 36, 40 years old, holding a PhD degree, and also not being single, yet still reporting conflict sometimes. And critically, as he suggested, it objectively showed that the lower a woman was in the scientific hierarchy comparing master's degree holders to PhDs to professors, the more likely she was to experience time-related conflict.
So it quantifies the hierarchy's impact.
Yes. It demonstrates the tool's usefulness beyond its typical traditional use in business, as in this case, in the study of a large social group. It's a really powerful example of applying complex problem-solving tools, data mining, to understand human systems better. It enhances our nuanced understanding of these societal challenges, letting us pinpoint specific areas of tension and maybe identify where interventions might be most effective, all with a high degree of statistical confidence. And again, thinking about the individuals navigating this, It clearly requires immense dynamic adaptation and personal robustness to manage these intense, often conflicting role demands, mirroring those qualities we discussed in the other complex systems, but on a very intimate human scale. Hashtag tag 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 outro.
Wow, what an incredible journey we've taken today. We've really spanned the gamut, haven't we? Through three vastly different, yet, as we've seen, surprisingly interconnected domains.
We really have.
We started with that truly audacious vision of a quantum AI, built on the foundations of ancient Kabbalistic principles. A system designed, theoretically at least, for hyper-personalization, for nuanced understanding, complex problem-solving, dynamic adaptation, robustness, coherence, all those things.
Yeah, seeing how concepts like divine reductions in garments could provide the literal structure for a quantum language, where everything from a letter's basic form to its dynamic interactions is governed by this inherent set of geometric and quantum laws, trying to build deep coherence right into the fabric of information itself.
And then we plunged right into the very practical, very challenging world of interspecies organogenesis, where biological design comes face to face with that formidable xenobarrier.
Such a stark reminder, wasn't it? That even with the most precise genetic blueprints we can devise, the actual combination of disparate elements in a living system, like human cells in a pig embryo, requires immense ingenuity and adaptation to overcome fundamental incompatibilities. Nature's own intricate designs, honed over millennia, just resist simple intervention.
Yeah, whether it's trying to match developmental timing or just getting cells to stick together properly without rejection, it really illustrated the inherent robustness, maybe even resistance to change in established biological systems.
Totally.
And finally, we explored that very real, very human struggle of the mother-scientist conflict, where societal structures, workplace expectations, and deeply personal roles often clash in the most profound ways.
And the insights from using basket analysis there are fascinating, showing how even these complex human systems, like the challenge of balancing career and family, benefit from sophisticated analytical tools to really understand their deep structures, to identify those specific points of tension or maybe points of support.
It really highlighted how individuals in those situations are forced into this constant state of dynamic adaptation, needing incredible resilience just to navigate systemic challenges that often feel, well, invisible or insurmountable.
And if you try to connect all this, look for the bigger picture. You can definitely see a recurring theme emerging, can't you?
Yeah, what would you say it is?
Well, whether we're talking about a theoretical quantum language, or the nitty-gritty of biological engineering, or the intricate web of social dynamics, the pursuit of coherence, of robustness, of optimal function, it always seems to require understanding and navigating these incredibly intricate interdependencies.
Right. Whether those interdependencies are based on divine principles or genetic codes or societal norms, the underlying challenge feels similar.
Exactly. Each field, in its own unique way, is grappling with these fundamental principles of design, integration, and adaptation. They're all striving to build systems, whether computational, biological, or social, that can somehow withstand disruption, adapt to change, and ultimately fulfill their intended purpose or function.
So after all that, what does this mean for you, our discerning listener? Well, perhaps it's an invitation to maybe look at the structures in your own life, your work, your relationships, the world around you through a slightly different lens.
Yeah, ask yourself, how are the different layers or systems interacting within your own experiences? Where are the gates and paths, maybe, that enable connection and flow, or perhaps inhibit it in your personal or professional life?
And maybe consider what reductions or clothings, those inherent boundaries, assumptions, or frameworks, might be shaping the reality you perceive. Are they limiting potential or providing necessary structure, perhaps without you even fully realizing it?
Which brings us to a final, maybe almost philosophical question to ponder. What if all these different forms of complexity we see, from the subatomic weirdness of quantum physics right up to the grand structures of society, what if they are all just different manifestations of a few universal underlying algorithmic primitives?
You mean like engraving, hewing?
Maybe. What if everything, everywhere, is constantly being engraved, establishing its fundamental structure, hewn, recursively unfolding its internal essence and logic, weighed, quantifying its form and value, exchanged, undergoing permutations and transformations, and combined, forming new compositions and emergent properties? Is there a universal grammar of complexity?
That is a truly provocative thought to leave you with. How might understanding these deep hidden structures, whether they're described in ancient mystical texts revealed in biological labs or analyzed in social data, how might that understanding allow you to perhaps consciously compose a more coherent, more robust, and more dynamically adaptive life for yourself?
Something to think about.
Definitely. We encourage you to keep exploring, keep questioning, and keep diving deep.